This is Lyrics, and welcome to today's session. In today's brief video, we are going to look at the term confounder. At the end of the video, you should be able to have satisfying answers to two key questions. One, what confounders really are, and two, how we can be able to identify these using statistical methods. And so we encourage you to stay right to the very end so you can benefit yourself. We equally encourage you to share the video with all so all can benefit. If you have not subscribed to the channel yet, why not pause the video and click on the subscription button? And if you're a returning subscriber, we appreciate you so highly for always coming here to learn. We encourage you to like the video and to share so all can benefit. Now, let's proceed. Now, the first major question we want to ask is, what is a confounder? The answer, a confounder is basically a third variable that distorts the apparent relationship between an exposure in one hand and an outcome. Now, this distortion of association leads to misleading conclusions, and so it is always important that appropriate actions are taken to address that. So how can one identify confounders? Well, the basic method that one can use to identify that is to review the literature. So you want to review the literature with respect to the exposure outcome relationship you're looking at and see what literature has to say with respect to potential variables that could impact that association. Additionally, there are three main conditions that must be met for a variable to qualify to be called a confounder. The first one is that it needs to be associated with the exposure, either causally or non-causally. Second, it needs to be causally associated with the outcome. And finally, it should not lie in the causal pathway between the exposure and the outcome. Once you have these three conditions met, then we can be certain that our variable is a confounder and potentially needs to be adjusted for in our statistical analysis. So basically, we have been able to identify what confounders are and how we can identify them using statistical methods, ascertaining that they have met all these three conditions, and also reviewing the literature. Now let's move to the stated platform so we can use a dummy data set to explore this confounder identification process so that we can really follow. Our data platform, and we're going to see how we can use statistical methods to establish a confounder. So here we have three variables: alcohol intake, age, and smoking status. So we want to see the association between age and smoking status. So our exposure here is age, and our outcome is smoking, whether you smoke or not. So the outcome is categorical, coded 0 and 1, where 1 means smoking and 0 means no smoking. And so we want to just have a look at that. So we tap at that and we realize it's never and yes. So when we add comma no label, we see that we have it as 0 and 1, never as 0, and yes as 1. And so we're going to run a logistic regression to establish the association between the age and the outcome. So logistic regression. So logistic, the outcome first, followed by the exposure. And then we run our logistic regression analysis. And tada, we have our p-value here stating that this is statistically significant. And so the association between age and smoking status is statistically significant. And specifically, with every unit increase in age, there's a 39.4% or 5% increase in the odds of smoking compared to non-smoking. So We now want to ascertain whether alcohol intake is associated causally or not with the outcome. So first of all, let's draw out this annotation. So here we have H. Let me change the color to blue. And so we have H, and then we have smoking, and we have alcohol over here. So we want to see whether there's a causal relationship between alcohol and age, and causal relationship between alcohol and smoking. So first, let's take the alcohol age one. So first of all, since age is a continuous variable, we want to run um, normality test to see whether it's normally distributed or not. That will inform us as to whether we will take the parametric version of analysis or the non-parametric one. So S week age. So we realize it is statistically significant, so it is not normally distributed. And so we need to employ the non-parametric version. So the parametric version of comparing age between a categorical outcome is t-test. But since it is not non-parametric, since it is not parametric and non-parametric, we have to use the Mann-Whitney U-test. So we have to run the rank sum test. And then we can do that. All right, so the result shows that alcohol and age are having association. So age is significantly associated with alcohol intake. And so we can see that there's a causal association over here. Now, how about, so over here, we can see it is years. See this years. And then, so how about alcohol and smoking status? We can equally do that using this line of code on the top. We add chi-square. Yeah, so here it is statistically significant. So there's association here as well. So now we are saying that alcohol intake is causally and non-causally associated with age. And then so this is the first condition, which is met. The second condition is that the variable should be causally associated with the outcome, and it's also yours. And then the third condition is that alcohol should not be in a causal pathway between age and smoking. Now, basic logic would tell us that age does not result in alcohol intake, and alcohol intake does not result in smoking. So we cannot have alcohol being in this causal pathway. And so we can conclude that alcohol in this sense is a confounder of the association between age and smoking. So basically, this is how we can statistically identify that a variable is a confounder using statistical methods. Now, it's important to note that once we are able to identify that a variable is a confounder, then there's a need for us to adjust it in our analysis. So when we run the crude analysis earlier on between the exposure and the outcome, we realize that our odds ratio is 1.39. So how about if you adjust it by adding the alcohol intake? What happens? So we see that the odds have reduced from 0.39 to 0.37. So we need to report this adjusted odds instead of this crude one. So basically, this is how you can be able to identify a confounder, and then you can be able to run the adjusted model if you realize it's a confounder of the association. If you find content such as this useful, we encourage you to subscribe to the channel, turn on the post notification bell so you do not miss any other video that will be posted here on this platform. Until we meet again on our next one, this is Catalytics, and it's a bye.